So good morning, good afternoon, good evening, depends on where you are. My name is Zhong Yiho. I'm the professor from the Chinese University of Hong Kong, and I'm also the Distinguished Lecture Program Manager of IEEE CEDA. Okay, so this is my great pleasure to have Professor Prabhat Mishra, okay, from the University of Florida to provide us the virtual distinguished lecture for IEEE CEDA. Okay, so before I introduce Professor Mishra, okay, let me provide some information to you. So currently in CEDA, we actually have 9 distinguished lectures. Okay, we have 9 distinguished lectures. They will cover different topics. Okay, so if you or your colleagues are interested to invite distinguished lectures to your local chapter or to offer a talk, or if you would like to organize a workshop or conference and you are looking for a keynote speaker, okay, please feel free to contact me or the distinguished lectures, okay, to your prestigious event. Okay, yeah, so today will be offered by Professor Mishra, and in October 10, there will be another virtual webinar will be provided by Professor Chen Zhuo from the Zhejiang University. So he will offer the virtual distinguished talk. Okay, so now let me introduce Professor Prabhat Mishra. Okay, Professor Mishra is a professor in the Department of Computer and Information Science and Engineering, and a UF Research Foundation professor at the University of Florida. He received his PhD in computer science from the University of California at Irvine in 2004. His research interests include design automation of embedded systems, hardware security, energy-aware computing, formal verification, SoC validation, explainable AI, and quantum computing. He has published 8 books and 35 book chapters and more than 200 research articles in premier international journals and conferences. His research has been recognized by several awards, including the NSF Career Award, IBM Faculty Award, and 3 Best Paper Awards, 11 Best Paper nominations, and the EDAA Outstanding Dissertation Award. He currently serves as an associate editor of Asian Transactions of Embedded Computing System. He is a fellow of IEEE, a fellow of AAAS, and a distinguished scientist of ACM. Okay, so perhaps the time will be yours. Okay, thank you.
Thank you, Professor Ho, for kind introduction. Good morning, good afternoon, and good evening, everyone. So today I'm going to talk about how to secure hardware for designing trustworthy systems. Here is a brief outline. I'm going to introduce why this problem is important, and then we'll talk about what are the hardware security vulnerabilities. And then I'm going to talk about, well, if everybody knows about the vulnerabilities, why don't they do something about it? I'll talk about that people actually do to design for security. But in spite of all of that, you still need to check, you need to verify whether the vulnerabilities exist or your design for security solution actually works. And if time permits, I'll take an example of an application-specific security. Then I'm going to conclude. So when we talk about securing system, or at least from the hardware point of view, then it have different layer. And this talk is not going to cover any aspect of software security. In hardware security, depending on your research area or your interest, it could be in the devices level, in terms of technology and their vulnerabilities, and it could be at the hardware architecture level. This talk is primarily focusing on that area, or it could be even at the systems level, where you are kind of at the intersection of hardware, software, and firmware, that kind of security issues. So this talk, as I said, is primarily focusing on this specific area. So before I begin, everybody will have a thought process, well, why do I care about hardware security? Because I already have some software solutions that I'm using, and solutions such as Security Enclave that gives you the protection from any kind of vulnerabilities. But I want to clarify one misunderstanding here is that all of these security solutions are built on the assumption that hardware is secure or hardware is the root of trust. If hardware itself is not secure, then all of these solutions fail. Now, as you know, if you have used any of them, ARM Trustzone, Intel SGX, TDX, AMD SEV, IBM also have a security environment. If you used any of them, you kind of then know that this security enclave gives you protection of about 10%. If you have a 64 core processors, about 2 to 4 of the processors are actually protected. So remaining 90% of the processor or whatever applications running on them, security enclave doesn't protect them. That's one. Most importantly, if you are following research in the trusted execution environments, you know there are so many attacks on them. So that can be broken either through normal attack or as well as side channel attack. So really, if you're trying to secure software through secure your application or trusted application at the software layer, it's not going to work. So really, where are the vulnerabilities then? So common vulnerability exposure or cve.org or cw.org, that kind of lists what are the vulnerabilities. If you publish a paper today in one of the top security conferences, it would be categorized by that Mishra and NIST corporation. And if there is a mitigation, it's nicely categorized. I kind of tried to get some numbers from there that focuses on electronic system vulnerabilities. By the way, there are many more vulnerabilities. So if it's a software only, other, unknown, hardware plus software, as you can see, it's a significant portion. If I zoom into hardware plus software, the kind of vulnerabilities is ranging from buffer error, permission and privilege, resource management, information leakage, and so on. So the attacker is trying to exploit one of these issues to mount an attack on a specific system. Now, why are all these problems happening? Why are these vulnerabilities? The story is academic community, the people like us, we have to publish something, we have to find an attack, but that's not really the point. If there is no vulnerability, you cannot mount an attack, right? So what is this story? Where is it starting from? So this is my view. So when I was doing PhD 25 years ago, so we were mostly talking about general purpose system or maybe a little bit of embedded systems. And then over the years, all this story kind of got defocused. Now we are going to talk about IoT and kind of cyber physical systems. So some of the features of embedded systems are still there, those complexity. Some new complexities are kind of arising. But bottom line is, there are diverse set of components, no matter how small they look, they actually has tremendous amount of computational ability, electronics and interactions, and they are not well verified, which I'll talk in a moment. So therefore, that opens up a lot of diverse and complex computing systems towards malicious attacks. And well, if systems are complex, why people not verifying? The people are not verifying is not the truth. People are. Again, if I go back to 25 years ago or 30 years ago when I was working in industry, then a product typically have 3 to 4 years. I worked in Itanium verification project. I worked in PowerPC verification project. So Intel, Motorola, many companies I worked, we typically have give and take 1 year for verification. Today, most of the systems, the total time is 1 year. If you think of your favorite phone, whether Samsung Galaxy or iPhone, it typically 1 year cycle. So in a 1 year cycle, you are not going to get 1 year for verification. And then that's basically puts you up. If you are designer or verification engineer, you are at the odds. But if you're an attacker, you have a lot of advantage because all these things are designed really complex, error prone, malicious communicating devices, and under extremely aggressive time to market requirements. So pretty much vulnerabilities are going to stay before it goes for production. And if you are not convinced, the most secure system that you are carrying, or most of us, except defense companies and defense areas, most sophisticated system we have is really your mobile phone. or we call it smartphone. It's not really smart. It's actually dumb from an attacker perspective, because if you look at the attack vector, the way that we can mount the attack are too many. I'm not going to get into any of them. I simply showing laundry listing that why it's an attacker paradise, depending on what access or how much access you provide, knowingly, unknowingly. Whether it's even as silly as if somebody knows how much battery you have in your phone, that can mount certain type of attack. Now let's try to get to the bottom of why so much of attack and what in the hardware is happening and what we can do about it. I will only scratch the surface so that it makes you excited in this area and you pursue research in this area. So let me just look at briefly, where are the security vulnerabilities coming from? And then we take it from there. So first starting point, let's talk about when you look at any electronic system, the brain of the electronic system is really a system on chip. And these days it's even getting better. We are talking about system on a package, in a 3D integration. But even if you look at 2D, the difference between this and normal integrated circuit is, in the past, you used to have one integrated circuit or chip for a processor, one for memory, one for DSP, one for analog to digital converter. But now you think about, you take all of them and fabricate one chip out of it. And that's known as system on a chip or system SoC. Now this SoC design is significantly complex, and not a single company can manufacture all of these components. If I am a system designer, let's say I'm a phone company, I'm likely to take my processor maybe from ARM, DSP from Texas Instruments, and many other components from many other companies who are based in those design. And I would like to put them together and test it. But the thing is, it's very difficult to ensure the thing. And I want to highlight, so we took one company chip, I cannot tell you, it's a router, but that router I was trying to plot where different components of the router that company purchased from. And as you can see, the components came from different parts of the world. That's a static view. If I show you a dynamic view, it would be a movie, Hollywood movie. So for example, one component is designed in California, and then it goes for simulation or synthesis in, let's say, in India. Then it goes to Taiwan for manufacturing, and then it came for testing to certain part of the Europe, and then it comes back for final integration in USA. So components are coming from different companies, and they are traveling across the globe many times. And then finally, the final product goes to the end user. And while all of this happening, in between, even if a component says, trust me on it, you are still supposed to check, what am I trusting? You cannot blindly trust. And there are so many components, so much of interactions, so little time to verify. That's where vulnerabilities just stay where they are. And of course, there are many vulnerabilities that are unique to that situation and that product and that context, which we don't know. If you don't know, then you can't verify really, even if you had time. And of course, not to mention, there are so many types of clones I got from different companies, and I had to write genuine and counterfeit. They look actually pretty much same. And in fact, sometimes counterfeit looks better than the genuine one. It's very difficult to figure out which one. So I took from car, from router, from camera. It's pretty much counterfeit is all over the world. And of course, counterfeit means vulnerability. Now let me look at one or two example vulnerabilities. That doesn't cover everything. One of them is hardware Trojan or malicious implant. And of course, as you know, in the hardware space, there are so many types of vulnerabilities, from piracy, reverse engineering, cloning, counterfeiting. But I'm just briefly going to talk about one of them, malicious modification in your design itself. That could be done by some angry designer. It could be introduced by your design automation tools. It could be completely unintentionally introduced, and that vulnerability got exploited by attackers later in the product lifetime. And how do hardware Trojan looks like? If you are from electronics background or EC background, it basically looks like the attacker should be able to figure out where are the rare signals. And using those rare signals or a collection of rare signal, it would create a trigger. And using that trigger, it would activate certain payload. And payload could be, for example, if certain signal is supposed to be true at some time, you make it false. Traffic light is supposed to be red at some time, you make it green. But when do you make it? That's the trigger. That's a rare scenario. You want to make it so rare, in a normal verification, people should not be able to catch it. So that's a simple combinational one. Sequential could be a specific count, you activate certain event. If you're from computer science background, then you can view it as a set of variables and a combination of variable. You want to use it as a trigger, as a rare condition, and to activate something. For combinational Trojan. For sequential Trojan, think of a finite state machine, an extremely rare transition. You want to use it as a trigger. And then whatever payload you want to do. If you're a system designer, the way you want to view at the system level, when you're putting components together, you are basically then going to insert a Trojan that is going to monitor some activity in the bus. And when you observe certain things, it knows, oh, at this point, the key or some information is unencrypted in the memory. Let me read it. So reading is payload, and looking for a specific activity in the bus is basically the trigger here. No matter how you look at it, finding a Trojan, even if I told you this design has a Trojan, is extremely impossible. In a tiny, silly, tiny design with 451 gates, has 10 to the power 11 possible Trojan. Even if I told you I have a Trojan which has a 4 input or trigger consisting of 4 nodes, it would need 10 to the power 11 possible test cases. Now you could imagine if I am given you million gate design or billion gate design, even lifetime of the universe will not be enough, and all the computing available in the universe to find that Trojan. It's extremely important and difficult to find. And there are a lot of works on Trojan detection, and there are books written, many books written on this. Side channel attack is basically, even if your design has no vulnerability per se, if you have access to that design, if you can find or look at the power trace, if you can download it, get it, then you will be able to mount an attack. Now you might say, well, why would I give you access to my device, and why would I let you connect your power probe to my device? Even if you don't let me in, if you are in a specific room, I can go to the next room, connect to the power outlet of that room, assuming you are the only one connected. Based on Kirchhoff's law, I'll be able to figure out how much power you are drawing. So there are a lot of attacks, but the point is, just by knowing how much of power your device is consuming, I will be able to figure out the attack. So here is a silly example. If I'm plotting how much of power you are drawing, I'll be able to figure out, okay, square operation is happening here, multiplication is happening here. Of course, this is a simple power analysis, and people would always try to hide this. Then you need differential power analysis. No matter whatever it is, the idea is power is only one of the side channel footprint. There are many other path delay, electromagnetic emanation, and there are so much of research area there. Given a device, can I mount a side channel attack based on any side channel leakage characteristics? Now, when we talk about side channel, these are physical side channel. In the community, there is also micro architectural side channel, and you are aware of Spectre, Meltdown. Those are at the architectural level. Those are the side channel attack at the architectural layer. But no matter what it is, your computation is correct, yet I'll be able to figure out what computation you are doing. I'll be able to figure out information that I'm not supposed to figure out. And also there are other structures in the design that are put in for a legitimate purpose, and attacker can exploit that. And in the mobile phone example, I tried to show some instance of those. So here is a one slide overview of how verification happen in hardware domain. So if it's before fabrication, whether VHDL, Verilog, whatever, gate level netlist, you kind of do pre-silicon verification. Once it's manufactured, there are typically two communities. One community do post-silicon validation and debug. Another community do manufacturing testing. So this community believes there is no functional error, but when manufacturing was going on, there may be manufacturing defects. You are trying to draw a line in photolithography, maybe that line was not drawn correctly, or two lines might have got connected. So whether bridging fault, open fault, so these are the communities, and different of these communities put certain structures in the design to help them. So for example, two common structures for manufacturing testing community, a common structure is scan chain. You want to initialize the state of the design by pushing certain values through the scan chain. The post-silicon debug community put trace buffer. Now, if I'm an attacker, I want to exploit this. What do I mean by that? My point is, there is no point putting a bulletproof door, front door in your house, which is doing exhaustive verification and security analysis and implementation, whereas an attacker can break the glass in your bathroom door and just get in. What was the point of that bulletproof door in the first place? So therefore, the reliability of a system is basically determined by the weakest component. And if an attacker can pretend as a legitimate debugging person and use the legitimate debugging facility to mount an attack, that is also a dangerous proposition. Now, the question is, okay, if I know about this vulnerability, if you know about this vulnerability, why people are not doing something about it? In fact, people are. There is a whole community out there, and broadly we can call it a design for security. And there are so many security kind of solutions that are out there as a countermeasure to defend against different types of attack. I'm going to just touch the surface by talking about only few of them. Cryptography and there are cryptography to kind of protect security, logic locking so that you cannot do reverse engineering and many other attacks, watermarking to say, oh, this is mine, physical unclonable function to kind of create a secure key and many other stuff. Let me just look at. So depending on which community you come from, this notion would be slightly different. From a networking community, we typically look at three areas. Authentication. If you are saying, if I'm saying I'm Prabhat Mishra, how do you know it's me? I'm on the phone. It could be my voice by some generative AI mimicking my voice. How do you know it's actually me? And then even if email is prabhat@ufl.edu, how do you know it's actually I composed and it's not somebody spoofed it as me? So that's the authentication issue. Then data integrity issue is if I am kind of sending an email to someone and say whatever information I'm sending, how do we know that that information will not be modified in the middle? So if I am sending somebody I love you, how do I know somebody not changing that love into hate? Of course, if it changes to something random, the recipient will figure out. So, but that's the data integrity. Data is getting altered. Privacy is I don't want anybody to know what I'm sending. How do we make sure that happens? Of course, there are solutions, and as you can, there are authentication solutions. I'll talk about. There are privacy related solutions, encryption. There are data integrity solutions, and by the way, the thing I talked about at the beginning, trusted execution environment, that also provides some of these solutions: code integrity, data integrity, and so on. So encryption plays a major role in the society to address privacy issue, but those encryption solutions can be broken too using side channel attack. Those of you are following the side channel community, the encryption community, something got broken, then elliptic curve cryptography came in, then that got broken. So people came with post-quantum cryptography. The day NIST announced the two famous solutions, there are so many researchers showed that can be broken through side channel attack too. So nothing is actually secure, but nonetheless, that is a solution for privacy. Then for authentication, whether single factor, just password, biometric, that's really an authentication kind of solution. Watermarking, there are a lot of solutions, but this is my favorite solution. So Steve Jobs, the Apple founder, was so pissed off with this company, Franklin Computer, who is stealing carbon copy of everything from Apple, and every time they have to go to court and prove to the judge. So Steve Jobs did this on the firmware. They had this kind of screen print. So basically, in that court appearance, basically they asked the Apple team asked the judge, press that button on the Franklin computer, and they press that button on the Franklin computer, which displayed stolen from Apple. That's an watermark. And of course, the the people who are copying, they actually don't know, because if they knew what is going on, they would have developed on their own. So that's the notion of watermark. You want to put it mark so that you can tell this is my IP, my product. And if somebody steals it, it's easier for you to prove. But it's difficult for the people who are trying to copy or use as their own, difficult for them to identify. So whether there are vulnerabilities or whether there are design for security solutions, you still need to check and verify. A vast majority of my career is centered around the security and trust validation. So even if you designed a design for security solution, you want to make sure that solution actually works. So you need to verify. So either way, you need to verify that the presence or absence of vulnerabilities. And I'm going to briefly touch upon some of them, the different categories. How do you verify in simulation? This should be easy for most of you because you are already verifying your systems for functionality. I'm going to tell you what is the bare minimum difference from that. From a bug model or your fault model, you change to a threat model, then your same simulation framework will work. Same thing for side channel analysis. Can I do, instead of side channel attack, I want to do side channel analysis to see if there is a side channel vulnerability. And then, of course, we can use some formal verification technique in many scenarios. And of course, machine learning, AI is all popular today, and people are using that also for vulnerability analysis. So before you do simulation, as I said, you need to know what vulnerability are we checking, or your threat model. If your threat model is not enough, then any guarantee you give is meaningless. I listed some of these. These are for, remember at the beginning, I showed common vulnerability enumeration web page. And some of these work is essentially Professor Yang Liu's work, and I saw Yang Liu in the audience list. And so basically, let me show you an illustrative example of two of them working together, information leakage and hardware Trojan. Here is a simple circuit. And in this simple circuit, let's say this is an asset. This is not a primary input. Think of the design is really big. This is some in-between signal. Ideally, this signal or this value should not propagate to the primary output in a normal situation. Now, if there is a Trojan, a specific trigger, which kind of makes this information flow from a specific area to this one. Now you might say, well, why is such a path the designer created? Remember, in your original design, there might be an if statement. If privilege level is equal to 1, then you want the key to transfer for a legitimate purpose. Now, during normal computation, that privilege level should not be 1. But what this Trojan is doing, it's changing that variable from whatever value it is to 1 so that this information flows to the output. And then attacker has access to the internal data. But assumption is during design time, attacker was able to install the Trojan either physically, or there are also at work on laser fault injection and all that stuff that you can actually do it even later, even if you haven't installed during design time. So what can you do from a simulation perspective? A simple example would be you can have some assertion statement during simulation time that would check the behavior you don't want to happen. For example, in this design, two components requesting, two requests, and there are two acknowledgement line. But if you have only one resource, let's say one printer, then you want only one of the line to be true at the same time. But so that's why in your design, you want to put this assertion. Now, of course, you say, why do I don't check completely? When I talk about formal verification, I'll argue in favor. You want to check this property for eternity. Sometimes due to state space explosion, you cannot check it. And even if you do check it, you may still want to have this monitor during runtime think of traffic light becoming green from the both side at the same time, so that it's instead of becoming green, it can become flashing red on the both side. So this is basically the assertion you want to put in, and during simulation you want to check. And when you deliver, you can just get rid of the assertion if you want. And there are a lot of work in this space. So I talked about ledger fault injection. This is an example. Let's say you have a finite state machine where it's supposed to check password, sorry, get password, check password, and then privileged state perform some operation. Now, if you look at, no matter how you implement your design in hardware level, whether binary encoding or one-hot encoding, whatever it is, if you have 3 states, it's going to have some kind of state encoding, 0, 1, 1, 0, 0, 0. If you look at the encoding, it's really, if a ledger fault can flip this bit 1, then you are already in this state. You might be saying, if you're from computer science, you might be saying, well, I don't understand this. How can you go from here to here? Because then you have to understand how it's implemented. It's implemented as a register and a logic. And register, whatever value that register element has, let's say this value is 0, 1, then this logic will perform certain function and update this one accordingly. Through a ledger fault injection, if it can flip this bit, by the way, that's possible in today's technology, irrespective of which layer this thing is. So if you can change it to 0, 0, then really the system has entered this particular state, and you can do any kind of attack that you want. You have the privileged state. Now, how do I check all of that? The problem of checking this, what is industry doing today? They are checking all the expected behavior. You know why they are not doing unexpected? If you have a finite state machine with n states, typically order of n transitions, it's easier to check. Actually, it's difficult to check, but order of n is still kind of linear. But if you think of n states, the possible transitions are order n square. So the transitions that doesn't exist, nobody is checking because there are too many of them. A single assertion can check that for you. All we are saying, from G to O, there should be no transition, no matter what and how many ways it's possible. There should be no transition. And anytime there is a transition, this assertion will fail, and the simulator will say, uh-oh, here is a sequence where it failed. Now, as I talked about, that side channel attack is a dangerous proposition from system reliability perspective, but you can use it to your advantage. Now, before I talk about it, think about it. What is happening today? What is happening today? You have a original design and then Trojan infected circuit. First question you will ask, wait a minute. If I have an original golden design, what am I doing with this? Remember, this could be your initial VHDL Verilog code. This could be your synthesized code. This could be the code that has traversed all over the world and all kind of stuff happened to it. And this is the one you want to manufacture or fabricate. So you want to make sure this one is golden. So this one you are not sending for fabrication. You can apply tests. And as we talked earlier, the number of test space is exponential. If you have a design with 200 inputs, total possible inputs is 2 to the power 200, which you cannot just apply all these. I don't know. That's not even trillions. That's like, I don't know what number that is. But the key idea is if you apply an input, check if there is a output difference, then you know there is something funny. Now, I didn't talk about, but Trojan doesn't have to be a functional Trojan. It could be non-functional, but even if functional Trojan, trying all possible inputs is not feasible. We talked about. So therefore, trying logic testing or simulation-based validation for Trojan detection is not a great idea for any normal design. Silly design, tiny design, sure. How about side channel analysis? So for side channel analysis, you can apply some input. We don't care about what input. Then we compare the side channel footprint. And if this footprint, there is a difference, we kind of say, oh, there is something funny going on. Now, the problem is, if there is a Trojan circuit is like few gates, and process variation is anywhere between 1% to 10%. So even if you, in a million gate design, even if you have 1,000 extra gates, you will not be able to see anything. You can distinguish that beyond expected process variation. So it's very difficult to detect tiny Trojan. So what we can do is, there are a lot of interesting solutions in this area. Can we generate interesting tests that would maximize activity in the suspicious area. Of course, we don't know where Trojan is, and minimize activity in rest of the design. Then we might be able to do we might be able to activate the scenario. So basically, think about, I'm trying to land my plane in a specific city, but I don't know where that city is. But let's say that country's president decided to turn off the light of every part of the country except that city, then I can land. So this is a similar analogy. You maximize activity in the suspicious area. So any side channel footprint that's coming and comparing, it's dominated by that area. So then you can detect it. And if I want to do little animation, let's assume a Trojan is constructed using these two nodes. But of course, in real world, you won't know that. But even if you do, if you try to run any test cases, lot of gates will switch. So blue gates are non-rare gates or non-suspicious gates, and suspicious gates. Even if your Trojan activates, so many other millions of gates are switching, they will contribute to your power footprint. So you won't know the difference. But if we can magically come up with a test where some very small number of regular gates are switching, then that would create a nice footprint in the original versus Trojan infected design. I'll briefly talk about the formal methods. So basically, formal methods area is basically all about, can we mathematically guarantee there are no problems? So I'll take something from my comfort zone of embedded systems. This is a silly embedded systems, which has basically start state and end state. And it runs only two programs, task 1 and task 2. Each program it can run in 0.5 volt or 0.9 volt. Depending on what it does, it has a different performance, power, and energy and temperature footprint. As you can see, if it takes this particular path, it's basically will take 21 microsecond, 31 millijoule, and temperature would be 80 degrees centigrade if it started with 70 degrees centigrade. So different path has different kind of computing paradigm. And in this example, let's assume the one shown in the dark black is the path that satisfies all the budget, energy budget, power budget, real-time constraints. So an attacker, really what an attacker needs to do is make sure that the dynamic voltage scaling routine, instead of running this task at 0.5 volt, it runs at 0.9 volt. Then it's going to take a different path and it would violate the real-time constraint. And if it's a safety critical system, it would have a catastrophic consequence. So really the property that you want to write a property and to check that the path does not violate that thing. First of all, is there a path in the design that satisfies all the constraints? If there is no path, you have to redesign. And if there are paths, can you disable those paths? So there are a lot of solutions. So detecting is one, then what do you do about it is the second issue. Then there are story of equivalence checking. This assumes you have access to both you have an implementation and you also have a golden specification. And many times in the design cycle, this doesn't exist. Then you cannot solve this problem. Even if this exists, let's say you have a C or some system C kind of model, and this is your VHDL, Verilog, or gate level implementation. If you want to do equivalence checking or SAT-based equivalence checking, you can put an XOR gate, convert this whole computation into satisfiability solution, and then give to a SAT solver. If SAT solver says it's satisfiable, that means it's found an output when it's 1. XOR output is 1 if two of the inputs are different. That means there is an input scenario that would make them different. Unfortunately, when you are dealing with millions of gates or million lines of code, none of today's equivalence checking tool will work unless these two designs have similar structures. So then we can do a lot of interesting things. When you cannot solve a problem in Boolean domain, you can map it to polynomial domain. And you can do Grabner basis reduction. And then if they're equivalent, remainder would be 0. If they're not equivalent, then you can use the remainder to kind of figure out and localize the bug. And we have shown in case of arithmetic circuits, we can magically find where the bug is. We can actually change it and fix it and give you the fixed solution. Of course, this works under assumptions of where Grabner basis reduction applies. It will not apply to any random design you want to provide. So as I said, machine learning is very popular. I want to take two quick examples. So malware detection, malware ransomware detection. Basically, you can use different data from hardware trace buffer, hardware performance counter, or any kind of electromagnetic footprint. And then you can use that for detecting whether there is a malware or ransomware. And there is a lot of work in this space. You can also do Spectre and Meltdown. I talked about architectural side channel attack. You can also do that using machine learning. And the way it works, if you choose the features correctly, and machine learning model will be able to figure out, well, if the features looks like this, then it's malicious. If this, then it's normal. Remember, attacker knows what we are trying to do. If attacker knows, then attacker will try to hide the behavior. Let's say you are looking at, okay, branch miss rate less than 4%. Okay, I'll create fake branches if I'm an attacker to change this number to more than 4%, and then this should look like a normal computation. And that's what happened for evasive malware. If I'm designing malware, then if you look at it, it's kind of all over the place. The green one, green dots, all over the place. Now, the thing is that also can be solved using machine learning. You might say, okay, what's the magic? Remember, I'm showing it to you from a specific perspective. If I keep rotating it, change the perspective, maybe there are complex space where they would look different. And there are, again, a lot of solutions. How do you detect those? Now, I have 1 or 2 minutes. I'm going to just talk about application specific security. All these security properties we talked about and applied, depending on the application domain where you apply, it would look different. So this is little old. Those days, even a baby can hack cars and do whatever they want to do. I want to talk about what are the security issues here in case of automotives. If you don't want to deal with security, be like me. When I go to India, I use Ambassador car. The company stopped manufacturing 2014. This is a 1958 model. They never changed the model. It pretty much has no electronics. I may die by parts falling down, but not through an attack. And the reason attack happens in today's car, no matter what you think about your car, it has tons of electronics all over the place. And they are not secured at all, or most of them are not secure. And on top of that, most of the cars, it doesn't have to be the fully autonomous car. It has a lot of machine learning models running in your car, either some stuff running in the car, something happening in the cloud, and update happening. So it's not just electronics, it's also AI, accelerators, interaction with cloud. There are a lot of parties getting involved, and there are a lot of vulnerabilities you have to deal with. And to make it matters worse, the car company don't care about security. They have ISO 26262. They call it functional safety. Even if there is a security attack going on, car is not going to stop at the middle of the street when running at, I don't know, 80 kilometers or 80 miles an hour. It's not going to stop. It's probably going to slow down, go to the side of the road, and then stop. So the passenger safety is a key important feature for cars. It's not the security key important feature. So there are these conflicting requirements and expectation. And the last thing that I have to mention, that these days cars are becoming better. Cars were not designed for security attacks. And you have to consider a typical car. I drive for at least 10 years before I exchange. Somebody is going to buy that car, drive another 10 years. That's 20 years right there. And when that car was designed, or it got approval from FAA or whatever approving authority, that another 5 or 10 years. So you are looking at a lifetime of anywhere between 30 to 50 years for a car. So any security mechanism you put in 30-year-old technology, that's obsolete 30 years later. Even the kid who was not born, might be the day they were born, they will be able to hack it. So that's why, depending on the system and their constraint and their lifetime and the assumption, it could be attacker's paradise. So that brings me to my conclusion. So basically, security attacks from a hardware layer is attack goal going to constantly change. New and new attack surface are going to appear, and the attacks, there would be a lot of known attacks, and there would be a lot of interesting countermeasure. But the thing is, attacker knows you have this countermeasure, they will sophisticate their attack, you know that attack, you will come up with this cat and mouse game is going to continue. What can we do? So if I'm an end user, all I can do, I can lock my car, I can change my IoT password, don't keep the default password. If I do those stuff, because my colleagues are not doing it, so I'm one step ahead in the attack game. So an attacker is likely to attack a car that is not locked than my locked car. So even doing these simple things might protect me because other people are not doing it. But nonetheless, this story will continue, and this area is going to remain active in foreseeable future. There are a lot of literature in this domain, and I also published extensively in this area, including a lot of books. And if you have any question, I'll be happy to take. Thank you.
Thank you. Thank you for a wonderful talk. Yeah, it's very comprehensive. I did not know that you cover many topics in hardware security. That's very impressive. Yeah, thank you, Prabhat. Yeah, so we have one question from the audience. Can you look at the Q&A?
Yes.
Yeah.
So this is the comment that mine is little lower level than architecture. Yeah, that's correct. So at the architectural layer, I briefly touched it. There are many layers. I agree. There are many layers. I broadly divided into 3 layers.
Okay. Yeah, I hope this already answered the receivers question. Okay. Yeah, and perhaps I think it's very cool that you mentioned that you can work on the you can apply the machine learning methods for to solve the hardware security problem. So I'm not, but I think right now there are several AI applications, as you mentioned, like the automotive car, right?
Right.
Yeah. So yeah, and do you have any? I'm not sure what will be the current trend for those hardware security for AI applications, especially for this those so-called LLM applications. Yeah.
Right. So basically, there are 2 broad areas, and actually those are very big areas. One is and broadly they are called as trustworthy AI or verified AI solutions.
Right.
So the key idea is, depending on the domain, if you are applying, if you think of car, let's go to the car, my favorite car. If you go for the car, the key idea is when you have an AI solution inside it and all the detection, whatever it's doing, that there is a person in front and the stopping distance and the road condition, all that it's trying to detect and taking decisions. So then question is, the AI, what are the things that can go wrong? Either it did not see that scenario, like the Tesla attack, where there is a cloud behind it and the person wearing the white shirt, and that scenario AI was not trained for. So this unforeseen scenario, what can you do? So the verification problem is basically creating scenarios and looking at, so this is same analogy as in normal domain. You apply different test cases and you see what happens. Then problem boils down to, is it enough test case? The scenario you are testing, is it enough scenario? Then there is a community which says, what kind of guarantee you can give for unknown scenarios? So there are different ways, and the analogy is actually same, because I can talk from 3 layers. You can look at AI hardware as a simple hardware, or AI software as a simple software verification problem. Or you can look AI as, okay, it's only detecting, is it a cat or mouse? Is it a human or a normal street? Is it a road print or a normal human standing? It's only making a distinction. So it has a choice of making a lot of errors, yet not having an accident. So that's actually an advantage from an AI. In a normal solution, 2 plus 3 has to be 5. It cannot be 6, 7, 8, 9, 10. But here, even if it's 6, 7, 8, 9, 10, and you are still classifying it as a human standing in front of the car, that's good enough. And also in the community, when you're verifying AI, like in real-time systems, it's not important when you are considering a robot hand, It's not actually important that both hands moves exactly same amount in this direction. What is important is if this one moves less, this should move more. So really the guarantee checking is not a line, it's really a cone. As long as solution is inside the cone, then you're fine. So all the AI solutions is essentially trying to figure out, are the solutions within that error tolerance level? And depending on the card, depending on that. So basically most of the AI techniques or AI verification technique or trustworthy AI techniques, but many people mingle a lot of things. Many people, fairness also they call it a AI failure. So bias also they call it as a failure. But from this webinar perspective, we are not considering them. But if you consider them, then space is even huge, AI verification space or trustworthiness. Because for their definition, if you are kind of discriminating between an applicant of certain gender versus another gender, that's a wrong AI decision happening, and it's because of AI or LLM. It's kind of cheating. So therefore, that need to be verified. So then that you can define that as a vulnerability. Discrimination is actually a security vulnerability. If you define that way, then basically it becomes an AI solution. And there are a lot of programs in many funding agencies on trustworthy AI, verified AI, and there are many research groups. So that's a very active research area.
Yes. So many people work on that. Yeah. Okay. Good. Yeah. Thanks for your reply. And I think we can take one question from Nikhil and look at the second one. Is anyone exploring the redundancy? That question. Yeah.
So redundancy for protection. Okay, so yeah, thanks, Nikhil. Redundancy is one of the solution. In fact, that's the basic principle of most safety critical system, like the airplane we fly. But the catch is, in the redundancy, you cannot put exact same component, because then the likelihood of both failing exactly same time is high. So fault tolerance I did not cover here, but fault tolerance is a huge community, and you can argue fault tolerance and security vulnerability can be clubbed together. So that's also an important consideration. And then let's take Himesh. Is it some kind of approximate that such an AI is doing? So Himesh, can you unmute and tell me what is your context? Which AI you are referring to for approximate computing, so that I can answer you?
Yeah, can we unmute Himesh? Or attendee cannot speak. Yeah, okay. Thanks, Laura. So
Himesh, can you type the context, please, so that I can answer?
Yeah, I actually have the same question with Himesh. When you reply that, it's very similar to the approximate computing. Yeah. So you don't need the exact solution like that.
Okay, so no, actually, I need an exact solution, but it's just that the solution in AI domain is slightly different than the classical domain. That's why I took the example 2 plus 3. I still need it to classify that whether it's a cat or dog. I want that to be correct. So, but it's just that the in between numbers it's computing, as long as it falls into certain class. So if you are looking from in between number computations, then it's approximate computing. But if you are looking at the final prediction value, it's not an approximate computing. Result is still accurate. Result has to be accurate. Because if result is not accurate in 99% of the time, then what happened to that 1% zone? Somebody's life is at stake during that 1% of the mistake time. So Nikhil had, there is more question. He may put the context. Yeah, that's what I. Okay, and then Nikhil, is this an original ambassador or mark? Look, the ambassador I take, that pretty much has broken glasses and lot of rust all over the place. Whatever I find on the online, I got it. And that's the only thing I get in my train station. So that's what I take.
Yeah. Okay. So I think we are almost 1 hour. So if there's no more questions, so I really appreciate Prabhat to give a very wonderful talk for today. Okay, thank you, Prabhat. And I think thanks for everyone to join this virtual distinguished lecture. Okay, so please note that on October 10th there will be another distinguished lecture. Okay, so we hope to see you. Okay, next month. Okay, thank you, Prabhat. Thank you. So
Thank you, everyone.